This video was sponsored by Let's Get Rusty. Here's a program used to render and zoom into the Mandelbrot set. As you can see, rendering each frame takes some time. Since my computer has multiple cores, I can spawn multiple threads and split the workload into regions, so each thread renders a portion of the fractal, significantly improving performance. Threads are one of the most important tools in programming. They can be the most useful tool you ever use, but if you misuse them, they can quickly become your worst nightmare. Even when your logic is perfectly valid, you can still run into problems like the ones shown here. As we've discussed in previous episodes, most operations and lines of code we write are not executed atomically. Instead, they are broken down into multiple CPU instructions. When multiple routines, running concurrently or in parallel, try to access the same data, problems can arise. One routine might read or modify the data, while another hasn't finished updating it yet. This leads to programs working with invalid data states, causing undefined, seemingly random errors that are extremely difficult to debug, especially because they're often impossible to reproduce consistently. And the worst part is that there's no purely software-based solution to this kind of problem. So today, we're going to take a brief look at how hardware supports software by providing primitive synchronization tools. Hi friends, my name is George, and this is CodeCrafters. When working with concurrency, there are parts of our code where multiple threads need to access the same data, such as variables or files, at the same time. This portion of code, where a race condition can occur, is called the critical section. The technique used to avoid race conditions is called thread synchronization, because the goal is to bring multiple threads into a consistent timing agreement with each other, both in when things happen and what data they observe. This ensures that threads can still run concurrently, while preventing their critical sections from overlapping. Before we continue, I want to mention that there are 2 videos on this channel that I highly recommend watching if you're not familiar with race conditions. In one of them, we tried to solve race conditions using only software, with clever algorithms like Peterson's solution, only to discover that this approach doesn't hold up on modern machines. At a high level, Peterson's algorithm should work because, for a thread to enter the critical section, a loop must be broken through a condition, and the conditions across threads are mutually exclusive, meaning they cannot both be true at the same time. So only one thread can enter the critical section, while the other remains stuck in the loop until the first one finishes. However, this synchronization mechanism is not guaranteed to work on modern systems. That's because modern processors can fetch many instructions at once, place them into a pipeline, and reorder them at runtime through a low-level optimization known as out-of-order execution, which is designed to improve performance. Here's a classic example that shows why that reordering mechanism is a problem when working with threads. We have this program with 2 threads. The expected behavior is that thread 1 prints 100. After all, since the initial value of flag is false, the while loop in thread 1 runs until thread 2 sets the flag to true, which happens after it set x to 100. However, since there are no data dependencies between flag and x, the processor may reorder the instructions in thread 2, executing flag equals true before x equals 100. In that case, thread 1 could exit the loop and still read x equals 0. Even less obvious is that the processor may also reorder operations in thread 1, loading x before checking flag. If that happens, thread 1 could still print 0, even if thread 2 executed in the correct order. As a result, any algorithm that relies on strict instruction ordering can break. In Peterson's solution, for example, it's crucial that certain lines execute in a specific order, but with out-of-order execution, the processor may rearrange them, completely breaking the synchronization mechanism. Since software alone cannot reliably solve the critical section problem, hardware must provide additional support. Most processors offer 2 features to handle race conditions. Let's start with memory barriers. Computer architectures provide special instructions, known as memory barriers, also called memory fences. These instructions ensure that all memory operations before the barrier are completed and visible before any memory operations after the barrier are allowed to proceed. This might sound complicated, but in simple terms, a A memory barrier is a special instruction that tells the CPU that no memory operation after the barrier is allowed until all the pipelined memory operations before the barrier are completed. From another point of view, and to our concern right now, is like we are telling the CPU, do not reorder memory operations across this point. Reordering can still happen among instructions before the barrier, or among instructions after it, but not across it. Believe it or not, this simple instruction is enough to make certain synchronization algorithms work correctly. In our previous example, we can insert memory barriers to enforce the correct ordering. In thread 1, a barrier ensures that flag is read before X. In thread 2, a barrier ensures that X equals 100 happens before flag equals true. Similarly, in Peterson's solution, inserting memory barriers ensures that operations occur in the order we expect. Now, here's where things get more interesting. On multi-core systems, each core typically has its own cache. If two threads running on different cores share a variable, each core may have its own cached copy. So what happens if one thread modifies that variable? Does the other core see the change immediately, or is there a delay? The answer depends on something called the memory model. More about that after a quick message from Let's Get Rusty. Have you noticed that more and more companies are including Rust in the development of their critical systems? That's not hype, that's happening. If you are thinking on leveling up your Rust skills, whether for personal growth or to land a job working on real systems, Let's Get Rusty is the go-to place for Rust training. Created by a fellow YouTuber and one of the most beloved names in the Rust online community, Let's Get Rusty has helped thousands of developers, myself included by the way, master the language and break into systems programming. They're running a new cohort very soon, and since spots are limited, now's a great time to check it out. Visit letsgetrusty.com/startwithgeorge, or just click the link in the pinned comment below. Big thanks to Let's Get Rusty for supporting the channel. And now, back to the video. A memory model defines what guarantees a system provides about the visibility and ordering of memory operations. Broadly speaking, memory models fall into two categories. In a strongly ordered model, a memory modification on one processor is immediately visible to all others. On weakly ordered models, changes may take time to become visible to other processors. This distinction is critical. Even if instructions are not reordered, if one thread updates a variable and another thread doesn't see that update in time, the synchronization mechanism can fail, and both threads might enter the critical section simultaneously. Because memory models vary between architectures, developers, especially at the systems level, cannot assume that memory updates are instantly visible across cores. To address this, memory barriers on multi-core systems ensure that pending memory changes are propagated in a way that makes them visible to other processors at the correct time. If you think about it, this is actually the core purpose of a memory barrier. The no reordering property is more of a consequence of what the barrier enforces, not its fundamental purpose. Memory barriers, however, come at a cost. They are expensive in terms of performance. For one, they restrict instruction reordering, preventing the CPU from executing instructions in the most efficient way. That may result in a cascade effect that disrupts other performance mechanisms, like the branch predictor, introducing further overhead. Also, even though memory barriers are effective and useful, they don't fit well with typical programming paradigms. When we write code, we usually think in terms of logic, not about how the CPU executes or reorders instructions. Introducing a memory fence to an algorithm doesn't really contribute to the logic of the program. It's more about controlling hardware behavior. For that reason, memory barriers are considered very low-level operations and are typically only used by kernel developers when writing specialized code that ensures mutual exclusion. Fortunately, for the rest of us, modern processors provide something much more practical: atomic instructions. These are hardware instructions that allow certain operations to execute as a single, indivisible step. If you look across different architectures, you'll find several of these instructions, but two of the most common are test and set and compare and swap. Trying to explain them purely in words is a bit awkward, so it's much clearer to look at them as if they were normal functions. The test and set operation, for instance, works like this. It takes the address of a Boolean, reads its value, sets it to true, and returns the original value. The important part is that all of these steps happen atomically. Normally, an operation like this would compile into several instructions, but with a dedicated atomic test and set instruction, the CPU performs the entire operation in one step, eliminating the possibility of being interrupted in the middle. Before continuing, keep in mind that this does not mean the function itself will automatically compile into that instruction. Rather, the instruction implements the same behavior as the function. So in practice, we explicitly write an inline assembly wrapper that invokes this atomic instruction. That way, every time the function is called, it reliably compiles down to the intended atomic operation. If two threads attempt to execute test and set at the same time, they will always execute sequentially in some arbitrary order. On a single core system, where threads execute by alternating CPU access, the operating system scheduler decides which one runs first. On a multi-core system, where it may allow threads to run in parallel, the hardware ensures the operation is still applied in some sequential order. Because this instruction is used to protect against race conditions, it must also provide certain memory guarantees. Before it executes, any pending memory operations must be completed so it operates on the most up-to-date value. And after it executes, its result must be made visible to all cores. Note that this operation alone does not solve the critical section problem. But because it is atomic, we can use it to implement mutual exclusion with very simple algorithms like this. We define a variable called lock that indicates whether any thread is currently executing its critical section. By default, its value is false. Notice that this variable is just a normal Boolean variable. There's absolutely nothing special about it. However, if two threads are about to enter their critical section at the same time, the operation that modifies this variable, on which the while loop depends, is executed atomically. There's no way to know in which order they will execute, but since we know the operation is atomic, we also know that only the thread that gets to execute it first will receive false, the value needed to break the loop and enter the critical section. The other thread will remain stuck in the loop, because by the point it is allowed to run test and set, the first thread has already flipped the value of lock. When the first thread exits its critical section, it sets lock back to false. Only then will the test and set in the second thread return the value needed to break the loop and enter the critical section. And there we have an example of using atomic instructions to implement mutual exclusion. Another common atomic instruction is compare and swap. Conceptually, it works like this. It receives three arguments: the memory address of an integer, an expected value, and a new value. It compares the current value with the expected one. If they match, it replaces the current value with the new one. Otherwise, it does nothing. In all cases, it returns the original value. Again, the key detail is that this entire operation that normally takes a lot of instructions can happen atomically with a single instruction. And for the second time, I highlight that this function doesn't automatically compile to that instruction. To make sure the instruction is omitted for this operation, we need to wrap it in an inline function. Mutual exclusion using compare and swap can be provided as follows. The synchronization mechanism here works in exactly the same way as the test and set algorithm we explored before. The only difference is that compare and swap uses the integer values 1 and 0 instead of booleans. The variable lock is initialized to 0, meaning unlocked. If multiple threads are trying to enter the critical section at the same time, the first thread that executes compare and swap successfully changes it to 1 and breaks its loop to enter the critical section. Since lock is now 1, any other thread trying to enter the critical section will remain stuck in the loop, because compare and swap will return 1. So, while one thread safely executes its critical section, the other is forced to wait. Once the thread exits the critical section, it sets lock back to 0, allowing another thread to enter. And that's how atomic instructions can be used to implement mutual exclusion. However, mutual exclusion alone is not enough to fully solve the critical section problem. To illustrate this, imagine we place this code inside an infinite loop. Here, Two threads are constantly competing to enter the critical section. The use of test and set guarantees mutual exclusion, as we explained before. But once a thread releases the lock, it immediately tries to acquire it again, and in many cases, it will succeed before the other thread even gets a chance. And then it happens again, and again, and again. For timing reasons outside our control, like how the CPU scheduler behaves, it's entirely possible that one thread keeps winning this race indefinitely. As a result, the other thread may never enter the critical section. So even though these algorithm guarantees mutual exclusion, they don't fully solve the critical section problem. Any correct solution to the critical section problem must satisfy three requirements. Mutual exclusion. If a process is executing in its critical section, no other process can be in its critical section at the same time. Progress. If no process is in the critical section, one of the waiting processes must eventually be allowed to enter. And bounded waiting. Each process must wait only a finite amount of time before entering the critical section. A solution that satisfies all three requirements looks like this. It looks complicated, but the idea behind it is actually simple. An array is used so each thread can indicate its intent to enter the critical section. The lock variable is still used to indicate whether the critical section is currently occupied. To enter the critical section, two conditions must now be satisfied to break the loop, and one of them depends on an atomic operation. This ensures that only one thread can break out of the loop, while all the others remain stuck until it is safe to enter the critical section, just as the algorithms we explored earlier. The key difference is that this algorithm introduces fairness. Instead of letting threads compete freely for the lock, it enforces a kind of round-robin order. When a thread exits the critical section, it checks if another thread is waiting to enter its critical section. If no other thread is waiting, it simply releases the lock, giving itself the chance to acquire it again. But if another thread is waiting, it explicitly gives the turn to that thread by breaking its loop. I'm pretty sure most of you will agree that atomic instructions are more intuitive than memory barriers, since our solutions rely on pure logic. However, this logic can quickly become a readability problem in real code. Imagine multiple threads sharing a counter. If we want to protect the counter from race conditions, we need to surround a very small critical section with all this synchronization logic, which makes the code harder to read than it should be. I mean, if I show you this code without comments or visual hints, how do you even identify the critical section? Since the tools we've discussed so far are low-level and not directly accessible to most application developers, operating systems provide higher-level abstractions built on top of them. The simplest and most common of these is the mutex lock, a tool designed to provide mutual exclusion. A mutex lock makes it possible to protect programs from race conditions with just two simple calls: acquire at the beginning of the critical section and release at the end. This way, no matter how small or large the critical section is, we avoid cluttering our code with complex synchronization logic. Mutex locks, as I just mentioned, are powered by atomic instructions. I was planning to cover the different ways they can be implemented, but this video is already long, so I'll leave that for a future episode. If you enjoyed this video or learned something new, please hit the like button. And if you want to learn more, subscribing is completely free. See you in the next one.